The formulas are pretty easy to remember for the disk method. The only thing that you have to make sure is if you have a horizontal axis of revolution, that you use this formula. If you have a vertical axis of revolution, you use this formula. Okay. So let me see if I can find us a good problem to look at. I mean, we could make up a problem pretty easy. Because if we take any area problem, we could make it a volume problem. But let's say that we had the line y equals negative x plus 1, and we wanted to find the area, or no, let's find the volume. Find the volume of the solid formed by revolving the region where x is greater than or equal to 0, less than or equal to 1, about the x-axis. Alright, so I have y equals x, and so let's see what that would look like if I graph y equals negative x plus 1 really quick. The easiest way to graph that is by using the x and y intercepts. Find the x-intercepts at the y equal to 0 and solve. Find the y-intercepts at the x equal to 0 and solve. So you're going to have a y-intercept of 1 and an x-intercept of 1. Alright, so this is the line right here. Now, if I was to take these rectangles from x equals 0, and they're an infinite number here. I'm going to space these out a little bit. Just imagine an infinite number of those rectangles, and I was to take those and revolve them about the x-axis. There's the x. So I would have a horizontal axis of revolution. Then I would form a lot of disks. Right? What would that figure look like? It will probably look about, if I was to turn it up on its side, it'd look about like this. Of course, the end would be circular, so it would be like a cone, right? You might could think of maybe like a top that you would spin, or a tornado, or something like that, a funnel, or a paper cup. Alright, now since I form these rectangles and I revolve about this x-axis, it is solid. There's nothing that's missing. It's not like it's going to have a hollow inside. Okay, it's going to be a solid figure. Okay. So whenever I set up my integral to find the volume using the disk method, volume is equal to pi times the integral from a to b. The a and the b, those are my x values. So remember, we want to look at the smallest to the largest. Well, we were already given that in the problem. It told us x is greater than or equal to 0, less than or equal to 1. So it'll be the integral from 0 to 1. Okay. Now the function. We want the function in the form y equals x, which we already have. So negative x plus 1 dx. So this will give us the volume of the figure that we would get if we revolved the area under this curve about the x-axis. Okay. So that's negative x squared over 2. I'm going to put the pi on the outside. And then negative x squared over 2 plus x. And we're evaluating it from 0 to 1. So it's pi times, it's going to be negative 1/2 plus 1 minus, plug in the 0, you get 0 plus 0. Okay. So that's going to equal negative 1/2 plus 1 is a positive 1/2. Positive 1/2 minus 0 is a positive 1/2. Times pi, that's 1/2 pi, or pi over 2. So the volume there will be pi over 2. Yes. Oh man, I just did the area. Yes, you do have the squared. I didn't do enough work, sorry. You should have stopped me. Y'all let me do all that work. Make me cry. Alright. X squared plus what? Or minus what? Minus 2x plus 1. It's good that it actually came out to be like this, because I'm going to show you a very common mistake other than not applying the formula. If you plug in a 1 right here, you get 1 minus 2 plus 1 minus, notice that plugging in a 0 here gives you an answer. Sometimes the function sets up so that plugging in a 0 gives you an answer, but a lot of times what happens is you get so used to plugging in 0 and not getting an answer that you just automatically assume that it's not an answer. So make sure that you don't do that. Alright, so we had negative 1 or negative x plus 1 squared. I didn't write this down, but that's negative x plus 1 times negative x plus 1. So that's where I got x squared minus x plus 1. Alright. Yeah, we do, don't we? So what is the integral? I was getting a negative answer. That's why I went back and looked at that. So what is this integral? X cubed over 3 minus x squared plus x. And don't forget what on the outside. Pi. Alright. So that's 1/3 minus 1 plus 1. Well, plugging in a 0 here gives you a 0. I got so happy earlier because before I integrated and I plugged it in. But I want to let you know that sometimes plugging in a 0 is not going to give you 0. So you have to be very careful with that. Here it does. Sometimes it's not going to. Alright, so what's your answer? Pi over 3. So let's see if we can forget about that one. since I made so many mistakes. See if I can wake up. Alright. And let's look at number 2 from the back of your section. On this in the book, looks something like this. Alright, so if we revolve this about the x-axis, then imagine what the shape would look like if we revolved an infinite number of these rectangles and formed discs. You know, it would be kind of a mirror. I mean, that's a very rough two-dimensional sketch of what it would be. It would be kind of like a bowl, I guess. It wouldn't really have a flat bottom, though. Maybe if you were to cut a football long ways, you know, that's what you would get, even though it wouldn't look like that because you'd just be letting the air out, but you'd have a figure that's in that shape. And so if we want to find a volume of that figure, since we have y equals x already, and this is a horizontal axis of revolution, we do want y equals x, so that's going to be what? You put your, where you have y equals, you put that part, your function, or the radius of each disk. See, this function is telling me the height of the disk at any point, and what that actually becomes whenever you revolve that rectangle about the x-axis, that becomes the radius of the disk. And so this function will give us the radius of any disk that's revolved. Don't forget to square it. That would be tragedy. And then after you square it, don't forget to integrate. I'm speaking from experience. Alright, so we need to square that. Remember, when you square two terms, you don't just simply square each term. You have to FOIL that out. You know, so that thing times itself, multiply. And so you'll get 16 minus 4x squared minus 4x squared. So it'll be minus 8x squared. And then negative x squared times negative x squared is a positive x to the what? 4th. Now my boundaries that I use, my upper and lower boundaries on my integral, come from x values. So this is the smallest x value, so 0. And then what's the largest x value? 2. Alright, and so now integrate that. So it's going to be 16x minus 8x to the 3rd over 3, so 8/3 x cubed, plus x to the 5th over 5. That's going to be evaluated from 0 to 2. Okay, so now plug in your 2. So it's going to be 16 times 2 minus 8 times, if you plug in a 2, that's going to be 8 over 3 plus 32 over 5, and minus, you get 0, 0, and 0, so minus 0. Alright, so it's going to be pi times, it's 32 minus 64 over 3 plus 32 over 5. One good thing about knowing that this is a volume is that if we get the wrong answer, like if we get a negative answer, that right away will tell you it's the wrong answer. You know, we did something wrong. So hopefully we do get a positive value here. Pretty sure that we will. It looks like the common denominator is going to be 15. So I'm probably going to have to break out the calculator here. I don't know what 15 times 32 is off the top of my head. So that's going to be 480 minus 5 times 64, 320 plus 3 times 32, 96. Alright, so I have 480 minus 320 plus 96. 256. So I have 256 pi over 15. That will be the area of that, the volume of that figure, cubic units. Alright, let's look at a problem where instead of revolving about a horizontal axis, we revolve about a vertical axis. So let's say that we had this figure. So we have y equals x squared just a U-shaped graph opening upward, should be symmetrical. Okay. And let's say that I wanted to revolve the region bounded by y greater than or equal to 0, less than or equal to 4, about the y-axis. Okay, so 1, 2, 3, 4. So this region right here. So we really don't even need this part of the graph. We're just taking this right here and we're revolving it about the y-axis. So that is a vertical axis of revolution. So what I'm doing is I'm taking horizontal rectangles like that, and I'm revolving them about the y-axis. So that forms a disk whenever you take a horizontal rectangle and you revolve it about a vertical axis, or a vertical, it doesn't even have to be the y-axis. It could be x equals 1 or anything like that. As long as it's a vertical axis of revolution, it would form disks whenever you revolve. So, if we have a vertical axis of revolution, we want our equations to be in the form x equals y. Okay? So I need to come up here where I have y equals x, and I need to solve for x. So what would I have to do? Take the square root of both sides, so I'd have x equals the square root of y. Normally I would put plus or minus the square root of y, but since I'm only dealing with positive y values, I only have to have the positive square root of y. Alright, so this function will give me the height of any rectangle, and the height of any rectangle is the radius of the disk that's made when you revolve the rectangle. Alright, so volume equals pi times the integral of r of x, that's the radius, capital R of x, but it'll be capital R of y, since we have x equals y, squared dy. And so this will give us the height of any disk, square root of y. Alright, so let's see what that is. The integral of, what's the square root of y squared? Y. So that becomes a pretty easy integral. What about my boundaries? Y equals 0 to y equals 4. 0 to 4. Alright. What about, what's the integral of y? Y squared over 2. I'm going to evaluate that from 0 to 4. So that's going to be, when you plug in a 4, 16 over 2, what is that? 8. And then plug in a 0, you get a 0. So 8 pi is the volume of the figure. Alright, let's look at this problem. This problem has 4 parts. And what we want to do is we want to figure out the volume of the solid that would be generated for revolving the bounded regions about the given axis or line. Okay? So we're going to start with, well, the way that you need to start this problem is you need to know what it looks like, what we're talking about. So you need to graph y equals 2x squared, just a rough sketch. Something like this. It does touch at 0, 0. Alright. And And then the line y equals 0, where is that? Y equals 0 is the x-axis. And then the line x equals 2. X equals 2, I'm going to pretend is about right here. So you see this region in here? I'll shade it. So let's pretend, I'm just making it a little bit larger than it is. Let's pretend that's the region there. And we're taking that and revolving it about a lot of different places. Revolving it about the y-axis, revolving it about the x-axis, revolving it about the line y equals 8, and revolving it about the line x equals 2. Alright, now let's just imagine what the figure would look like and try to sketch each one of these. So first, I'll put A. I just want to maybe sketch what it would look like once you do take that region and revolve it around the y-axis. So if it's around the y-axis, this was what the region kind of looks like. So it's going to be a mirror of that on the other side. So it kind of looked like this in 2 dimensions. And then you have to imagine that everything is just revolved completely around. So, you know, if I had to put a name on something like that, it'd probably look about like a water bowl or something like that for a pet, if you were to revolve that all the way around. Okay. Right, let's see what would B look like around the x-axis. So you have this figure here, and then you want to revolve that about the x. So it's going to be kind of a mirror of that figure here. And so that's going to be a solid figure. Is this figure on A, is that going to be a solid figure, or are we going to be missing some stuff inside? We would be missing some stuff, right? Because it'd be kind of like a bowl. The inside you'd be missing. So it's not going to be a solid figure like this would. This figure, because of the way of the curve, when we revolve these different rectangles, we'd be missing some stuff inside. Alright, what would C look like? Around the line y equals 8. I believe, let's see, if we were to, I want to take this and set them equal to see where they intersect. Let's see, no, it would have to be, you'd have to have x equals y to set them equal. So that would be, if you had 2x squared equals y, x squared equals y over 2, x equals the square root of y over 2. I want to set it equal to x equals 2, this line here, to see what y point this is, because I believe that is 8. Okay, I just want to double check and see. So if I set this equation equal to x equals 2, and I squared both sides, then I do get y equals 8. So yes, this is y equals 8 right here. So part C, that's what I'm revolving that figure about. I'm revolving it about the line y equals 8. So I'd have this figure, and then if I revolve it about this line y equals 8, I'm going to have a mirror of that figure like that in 2 dimensions. That's what it would look like. Alright, now, so it's going to kind of look like A, but in 3 dimensions it'd be kind of, like a bowl shape. We'd be missing some stuff inside. It wouldn't be a solid figure. And then D, about the line x equals 2. X equals 2 was this line, right? So if I revolved it about that line, so there's our figure, and this was x equals 2. So if I revolve it about that line, it's going to look something like that. Would it be a solid figure? Is there anything missing in there? You see the 2 solid figures up there? Which 2 are the solid figures? B and D. This is a very important part of today's lesson, even though it's near the end of class. As long as it's a solid figure, you're not missing any part inside, and so you work it exactly like we worked the previous problems. You set up your integral, say pi times the integral of, and then depending on whether it's vertical or it's horizontal axis of revolution, if it's a horizontal axis of revolution, you want the equation in the form y equals x. If it's a vertical axis of revolution, you want x equals y. Whenever you start missing stuff, though, like on A and C, we're just looking at that in 2 dimensions, so it's kind of hard to visualize what it would be. It would be kind of bowl shaped. But you're missing stuff on the inside. So it's not like the entire figure, you could form it by discs. Okay? Whenever you take, for example, look up here. Whenever you take, say, this rectangle right here, and you revolve that about the axis and get this part over here, this right here, right in there, you would be missing some stuff. So instead of a disc, you're actually making a washer. The washer, I guess you could call it the washer method, but it's an extension of the disc method. Let me show you what I'm talking about. I can show you a washer really quick from the textbook. You see here, if you take this rectangle and you revolve it about this line, and this is kind of turned on its side, since there's a space here between the line that you're revolving and the bottom of the rectangle, there's a space that's formed here. You're missing a piece. And so instead of forming a disc, you form a washer. And so instead of just capital R of x squared, the radius squared, the capital R of X is now going to be considered to be, it'd be like the area or the volume. It would be the radius of the disk that would be made. Okay? And then you have an inner radius from here where you're revolving to there, and you have to subtract that out. If you think about it, like capital R of X is the radius of the disk, the solid disk, and then lowercase r of X, that's like your inner radius. That's the radius of the missing part. If you subtract that missing part out, then you would just have the volume of the entire disk. And I may have said area, but I'm talking about volume. Okay? So capital R of X, you can think about that like your outer radius. The outer radius is going to give you, if you were to use that in a volume formula, that would give you the volume of the entire disk. Then this little r, or lowercase r of X, that's like your inner radius. If you take and subtract that piece out, the inner part, then that would give you the volume of the washer. And so any graph, when we revolve it about an x or y axis, or a line, x equals something or y equals something, if you're missing pieces, then you have to use the washer method. If it's a solid piece, then you can just use the disk method. And the washer method is just an extension of the disk method. Okay? So do you understand the difference between the disk method and the washer method? The disk method is used whenever you have a solid figure. You're not missing anything. No pieces are missing. It's solid. The washer method is just an extension of the disk method, and you use it whenever you're missing a piece, whenever something is not a solid figure. Okay? So that's what we'll pick